find the periodicity of sine t. We just did something very similar. So what is the period of sine t? Sine of t plus 2 pi is equal to sine t, which means period is 2 pi. Now for cos pi t, so wherever there is t, replace that with t plus some capital T. That's all we are trying to do. And in this case, if this capital T was 2, then this becomes cos of pi t plus 2 pi, which we know is exactly equal to cos pi t itself. Hence, this period is just 2. Now, what about rect function? What is a rect function? We know how it looks like. So this is a rectangular function, and no matter what value of t that you choose, this will not be true. So essentially what are we saying here? If you add plus t, it means you're time shifting the signal, right? So in all these descriptions that we have seen before, we are saying that x of t plus t should be equal to x of t. That means we are shifting the signal by some capital T, either to the left or right, and after that shift, it actually appears as if the original signal is there. The shift does not really matter at all. So there is some amount of shift that you can do, after which it appears to be the same signal itself. And this period of shift is what we refer to as the fundamental period of the signal. But of course, in this case, you cannot find such a shift. The moment you shift the signal by any amount, it will look totally different compared to this rectangular function that we have here. So you cannot find a t such that this relationship is true. So here this is aperiodic. Okay. Now what about e power omega t? So it's the same case. So how does e power omega t look like? As long as omega is positive, we'll have something that looks like this. So this is omega is positive, and let's say omega is negative. So if omega is negative, then we'll have something like this. Now in this case, once again, no matter what value of t you choose, this is never going to be equal. Of course, the only value of capital T that you can choose is 0, which does not really make sense. So then it's the actual signal itself, right? So this is never going to be equal to t for non-zero values of capital C, which makes this also aperiodic. Okay. What about e power minus j omega t? This is simple because e power minus j omega t plus 2 pi omega is equal to e power minus j omega t times e power minus j 2 pi t times e power minus j 2 pi, which is equal to e power minus j omega t. Hence, this is periodic with period equal to 2 pi by omega, which makes sense, right? So omega was the angular frequency, and we said the period is equal to the angular frequency. The relation between the period and the angular frequency is omega is equal to 2 pi by t. This is the relationship we had, and that's exactly what we are seeing here. Okay. All right. Now we have an interesting signal here. So what does this signal mean? So let us here assume first that t is greater than 1. Okay. Now let's say that t is equal to 2. Capital T is equal to 2. What does this mean? So let's draw this signal. The rectangular function for n is equal to 0 here is rect of t itself, right, which we know that is just half and half 1. Now let's put n is equal to plus 1, then you get rect of t minus capital T. We have to shift this signal to the right by 2. So this corresponds to, so let me do this. This corresponds to the signal that we have here, okay, and the center is 2, and this point is minus, sorry, this is 3 by 2, and this is 5 by 2. Okay. Now what if n is minus 1? So we have rect of t plus t here. And what does that correspond to? It corresponds to a shift of where we have minus 2 here, the same things. And this keeps going on, right? So we'll have plus t minus 2t, so on, and here so on. So this signal keeps repeating on both the sides. Okay, so as you can see here, n goes from minus infinity to plus infinity. So remember we said periodic signals has to be from minus infinity to plus infinity. So this is going from minus infinity to plus infinity, and we can find a period. So if you can look at this, from 0 to, let's say, observe the signal from in this window from 0 to 2. So you can copy whatever that is present here and then keep tiling it again, and that makes this a periodic signal of period 2. So not necessarily only this portion, you can, like I said, you can pick from anywhere to anywhere. So you can take this portion, or you can arbitrarily pick this portion. So you can pick any of these portions as long as this time period is 2. You will see that here you get x of t plus 2 x of t plus 2 is equal to x of t. So this signal that we have here is periodic, and its period is equal to capital T, whatever is that we chose here. Okay. Now what if t is 4? Then the period will become 4. So what if t is less than 1? Then what do you think will happen? So when t is less than 1, then there will be an overlap here. Okay, so this signal will overlap with the corresponding neighbors on both the sides. Okay, still it will be periodic, but the period will not be equal to t, it will be different. So we'll assume that t is greater than 1 in such cases, and then we'll say that the period is exactly equal to t. So whenever you have something like this, so remember what we have done is we have taken a finite length signal and then we have tiled it, right? So this is exactly what we did. We kept repeating it after certain intervals. So we made this operation of copying it and pasting it again and again, and that operation is given by this expression. So we can tile any finite length signal like this. So I can just replace this rectangular with triangle. Now I'll have a periodic triangular signal. So by doing this, any finite length signal could be converted to a periodic signal by this technique. All you have to do is ensure that this t that you chose here to be greater than the length of the finite length period.